So, hello and welcome to our online training for students. I welcome you, and now I would introduce myself. My name is Daniel. I am responsible for the human resources here at our Germany team, here in our German team. Moreover, I am also responsible for the customer support and the marketing here at Dlubal. So coordinating our video marketing team, especially the whole e-learning platform and so on. And today I will be your moderator and organizer for this online training, especially for you students. And today also on my side is Bastian. Bastian, maybe you could also introduce yourself.
Hello, my name is Bastian, and as Daniel already mentioned, I am also responsible for the customer support and marketing, and today I will support you during the training. So if you have any questions, you can ask questions and I'll try to answer them. And if some questions occur a bit more, we'll have the chance to ask them in public, so Daniel can answer them for all of you.
Thank you, Bastian. So Bastian will help me today and will be also the second voice here in this training. Now I would say, let's go ahead. So for those who are using the GoToWebinar platform for the first time, I would show you here the general concept. First of all, if you use the desktop application, it can look like that. So show or hide control panel. When someone can't listen us or hear us, just adjust your audio settings, maybe change your speakers, and then you can hear us. And if you have any questions, put that here to that box, and Bastian or me will answer it. Good. Then, what is the content of today? First of all, I will explain you the principal theory of the finite element analysis, or also finite element method. Don't be afraid, I don't make any lectures like in the study, just 2 slides of very basic theory of finite element method. Then I will introduce you to RFEM. I will explain you the general user interface, the general concept, the general functions where you can find what, and so on. Then together we try to model and calculate a continuous plate. You see it also here on the right side in the corner. We will model 3 different plates, and as a reference also an additional beam and 2 field beams, so a continuous beam, in order to compare the results here at this section. Yeah, this will be very interesting. We will also have different refinements of the FE measures, and then we compare the results of the bending moments. So then the next part will be the stability analysis of an Euler case 1. So we will have a beam, and at the end of this beam will be a support, and we will have a load on the head with some vertical and horizontal forces, and then we take a look on a clamped frame and do also an stability analysis there. Good. I will close my webcam because then you can see more of this presentation. And before we continue, we created this training a little bit interactive. So we have prepared some polls and some questions. And the first question will be if you work with 2 monitors or screens. So I will start this poll, and please let me know in order to adapt our speed of this training. Okay, then most of you have answered this question. So I close this poll, show you the results. So it's almost 50-50. So the one side work with 2 monitors or screens, the other one not. Don't. This is no problem. So I will adapt the speed for everyone. So I think this would be the best solution in order to do that everybody has something of this training. Furthermore, I want to point out that the online training will be recorded. So you will get the recording as well as the certificate if you have participated, and also the other materials like the models to download and so on. Good. So, basics of finite element analysis, or in Germany we say to that also finite element method. So, what do we have? Normally, most of the computer programs are based on the displacement method. Displacement method is the calculation method where the displacements or deformation are the unknown results. Normally, you learn also in the study the force method, where the force is the unknown and you solve the unknown force, and then you can recalculate the bending moments or the normal forces, shear forces, and so on. But the computer programs, they are using the displacement method because it's easier to implement these more convenient and more easier calculation for the programs. So if you look to any complex structures, it is normal that the analytical solution is not so easy. So it's hardly possible to calculate or to find any analytical solution. And this is also the reason why real structure are decomposed into a mesh of finite interconnected elements. And at each element continuum and at each node, the properties, so especially the degrees of freedom, like deformation or restraints, are described at the nodes. So the properties of the element continuum. So normally the finite element analysis is just a numerical approximation of an exact solution. So the mechanical behavior is described by approximation sets. And the whole process of the decomposition of structure into finite elements is called discretization. So remember that, this is very important. Discretization is the decomposition of structure into finite elements. Good. So what is the general procedure of a FEA calculation? On the right side, you can see this image with the basic steps. And first of all, what gonna do is the discretization. So we determine the local stiffness relations, the local element stiffness metrics at each node. So we mesh the structure, so we do the discretization. Then we transform it to the global coordinate system and assembly the whole entire structure. Then we have also to consider different supports in order that the structure is stable. So the boundary conditions are very important to define, and normally the boundary conditions are the support conditions. And then, as we said before, the displacement method is the method implemented in the computer programs. So at first we determine the displacement vector, and after that the internal forces like bending moment, shear forces, normal forces, tensions, and so on, stresses, strains, and so on. Yeah, and this is also called the solution of the equation system, and then we do the determination of support forces and internal forces. So this is the general and very short concept of FEA calculation. And now we start also the modeling in RFEM. Therefore, we have prepared 3 different types of plates. In this case, this continuous plate. And as you can see here, we have here this section with the bending moment, field moment, and support moment. And we try to take a comparison to that continuous beam here. Yeah, 2 field beam with this support and field moment. And there we can see also the similarity to the results. And it will be very interesting because we have different kind of refinements of the meshes. Here we start with the 1 meter mesh, then here 0.5, and here 0.1 mesh. But this is something we are going to do together in RFEM. So let's start with RFEM. Therefore, I have also prepared one question for you because I want to know how good is your knowledge in using RFEM. Okay, the most of you have finished this poll, so I will show you the results. So the most of you, of the participants today, are beginners, perfect, and also some other guys have already some experiences in using RFEM, also fine, because also for them, you can learn maybe some functions you haven't heard about that before. So I think for everybody, there's something new to learn here in RFEM. So let's go ahead. When you open RFEM for the first time, it can be possible that this window here will open, this general data window. If it's not the case, no problem. You can create a new model here when clicking here in the menu bar on File and then on the tab New, or also by clicking here this white sheet, New Model, or also by the keyboard combination Control and N. I will click here on that, and then the next step is here to insert any model name. In this case, I will enter continuous plate. Oh, sorry. (0.1) project name is, yeah, then you can choose here any project name, and here you can choose whatever you want. So normally I save it in my download folder. It's up to you where you save your files. You can create also a new project or new folders. It's completely up to you. And the next thing is the type of model. I think I put here continuous. Okay, now it's right, I think. Now you can here insert the type of model, or you can choose the type of model. So you have here the typical 3D model. For example, 3D halls, or also 3D massive structures like multi-story buildings, something like that. If you want to reduce the dimensions because you just want to watch any two-dimensional frame or something like that, then you can use this 2D model. So XY is for plates, for example, yeah, which get a vertical load. So the load is perpendicular to the plate. And the other one, the 2D XZ, is a typical frame of a steel hull, for example. Yeah. And this 2D XY is when you consider any plate and it gets any wind loads, for example. For our case, we choose here the XY direction because we are considering the plate with perpendicular loads. So we don't need any standard. This will be important maybe for the next parts of our online training. Also concerning the other trainings, because this series of trainings is divided into 3 parts. Today is the first part, next month is the second, and in 2 months is also the third one. Please join and register for the next parts of the training, and then you will also get the certificate and also the recording of the next parts of the training. Good. The orientation of the global z-axis is downward. Yeah, normally it's quite usual for structural engineers that we are looking downwards because of the loads who are acting downwards, and on the other side, the architects, for example, they are looking upwards, so they orientate the global z-axis upwards, but we as structural engineers normally downwards. So then, yeah, sorry, before I forget this, especially for people who are from America or who are using the imperial units, you can change here by clicking here at this icon the units, and we offer almost every other kind of units like feet, inch, yard, and so on. Just change it here. You can change it also for loads, results, and other dimensions. And yeah, if you have some people from America, you can change it here. Okay. Okay, let's begin. Click on OK. And now to RFEM. What is RFEM? RFEM is a 3D finite element program. And with this program, I can calculate almost everything. Yeah. So It's a powerful software for quick and easily modeling, structural analysis, and the design of 2D and 3D models, consisting of members, plates, walls, folded plates, shells, solids, and so on. And only with RFEM you can calculate internal forces, stresses, strains, support forces, and deformations. The whole design of steel, concrete, timber structures, and so on, you do with the add-on modules. Yeah, you find the add-on modules here on the left side at the project navigator, the data navigator. Here you'll find all add-on modules. And if you want to find out the ratio of any steel section, yeah, therefore you have to use one of these steel add-on modules, for example. You also find the add-on modules here in the menu bar for almost every kind of application area. Yeah, but more to add-on modules we will have in the next parts of the student training. Good. So I will explain you now the whole user interface of RFEM. You don't have to do it now with me because I will open now another project where I can explain you the whole user interface at an already existing project. So just watch and remark maybe some information. So I will open here this one. So fine, very good. I will activate here in the status bar the snap and grid function. So chronology. The chronological step is that we have here the menu bar, and here in the menu bar we have the possibility to do almost every kind of workflow function of RFEM. Yeah, the basic file, you can save, you can open, you can import, export, you can insert blocks, you can save it in the project manager, print, and so on. Yeah, I think this is known from other software applications. The next one is the edit function, also here in the menu bar. If you click on an object, at an object, and now you want to edit it, you can move it, rotate it, scale, or whatever. Yeah. Also, you find here additional information concerning the model data, loads, load cases, and combinations. The view, you can click here on loads, then the loads will appear, or clicking on the results, then because we don't have any results at the moment, the program asks me if I want to have the results, and I click yes. Now I see also the results, and yeah, also some other kind of things like comments, dimensions, and so on. Yeah. So insert here with this tab, you can insert almost every object from model data to loads and also to load cases and combinations. The general step in RFEM is that at first you model all kind of necessary objects. So you define materials, you define cross sections, materials, cross sections, and then you can also model members, hinges, and finally also nodal supports, for example. Then you create also your load cases and combinations, then your loads, and then you can calculate it, and then you have the possibility to watch the internal forces and the results. And this is the basic step in RFEM, calculating projects or doing some structural analysis projects and so on. Yeah. And the other bars here enables you also other kind of projects or functions. Maybe this one is very interesting. The options in the menu bar when you want to change the language. So especially for those who are maybe from Italy or from France, Spain, or something like that, we have the possibility to change here the language into, I think these are 10 or 11 languages. So the whole interface will change after you quit and reopen the program. Yeah, you restart the program. So Italian, Polish, French, these kind of languages we offer. And maybe you see also in the background, I use here a white background. Maybe for those who are open RFEM for the first time, you can change your background. Also here in the options in the configuration manager, you can change here the background to black or to white. At the moment, I use the white background, but when I double click on black background, it will change to the black background. You can also adjust here a green or a red background. Just use here the display properties and then or the other kind of colors, and you can adapt your background. Good. I think this is the this is everything to the menu bar. Yeah, under the menu bar we find the symbol bar. The symbols enables you a fast way of inserts of some objects or of some views or edits or something like that. So if I want to create here, for example, a new node, I click here on new node and I click here somewhere and I get new nodes and so on. The same also with lines, for example. I click here and then here. So this is, I think, pretty clear. Yeah. Now I will undo it. And I will also change my background again to a white background. Good. Yeah. Now on the left side, you also find the project navigator. It is divided into 4 registers: data navigator, display navigator, view navigator, and also the results navigator. So at the first one, the data navigator, you find all kind of objects, beginning from model data, continuing to the load cases, the loads, results, and so on. You can create their new objects, for example, by right-click on one node, edit node or new node. But of course, you can find all existing objects. So when I open here this tree structure, I see also here the already created nodes like this one. And if I click on that, I can't see it really in the model. No problem. I right-click on one node, I can find it, and a red arrow shows me where I can find this node. I have also lines here, nodes, surfaces, materials, and so on. Yeah, I think this helps you to have a good overview of your project, of your objects, but also a smooth way to create something like that. So if you maybe create a lot of materials or something like that, you can use it. Just click here on a new material, and then you can enter and insert a new material. Okay, let's jump to the next navigator. This is the display navigator. So in this case, I have here activated at the moment the loads. If I don't want to see them, no problem. Just click here on this loads, and all loads disappear. You can do the same here also on the symbol bar here, show loads, and so on. You can also disappear some kind of models, like for example the nodal supports. Just click here on nodal supports, and the supports disappear, but only in the visibility. And the same here also with the results, FE mesh. So when I don't want to see the FE mesh at the moment, click on that and you don't see it. Good. So far to the display navigator. Let's continue with the view navigator. Sorry for my bad spelling. So if you like kind of view, for example, this one, yeah, quite nice. Then you can create a user-defined view. Just click here on create new user-defined view, favorite. Okay, and when you rotate it a little bit, or you move a little bit away from the model and you want to have your favorite view again, just click here on favorite and it jumps back to your favorite view. This is a very big advantage, especially when you are doing some more detail or more complex structures or projects. Then you can use here this user-defined views. Good. And also with the help of visibilities, you can filter some things better. Yeah, for example, I just want to see all cross sections here of this concrete. No problem. Go to members by cross section, open this tree, and activate the rectangle 300 by 300. And only these kind of cross section are visible and are also possible to modify. Yeah, you can also click with right, and this menu appears, and then you can also click here on display model, show hidden objects in the background, so the surfaces here will disappear and it will look like that. Good. Undoing this visibility mode, you can click here, visibility by select objects, and click here on the arrow, and then cancel visibility mode. The same thing you can also do here. Good. Yeah, and now the last one, the last navigator, this is the result navigator. Here I can see the results like deformations, stresses, internal forces of members, and also the support directions. At the moment, I see the global deformation of the whole structure, also from the members and from the surfaces. If I just want to take a look on the members, I click here on members and choose the right internal force. In this case, I choose here the normal force, and there I can see also the compression forces and the concrete columns. Yeah, fine. Also here surfaces, internal forces of the surface, mx, my, and so on. Good. And also the support directions with the components px, py, pz, and so on. Yeah, good. So much to the navigator. Now, on the bottom of our user interface, we have also the tables. With the tables, we have also the possibility to view all information and also to insert and create new information or objects. For example, I can create here, for example, a new node. So I click here on standard. Reference node is my node here, and I enter here kind of coordinate. I click here on 14, y is 0, and z is 3. And I see here this created node. And this is also possible for almost all other kind of objects like lines, materials, surfaces, solids, and so on. You can jump to the next tables here by clicking to the next icons. Now I am at the load cases, nodal loads, or also member loads, line loads, surface loads, results, and so on. Good. Now maybe to the movement of the RFEM model. So with the middle mouse wheel, you can move your whole project. Yeah. By clicking the left mouse, you can create a selection window. And when you do it from the left corner to the right corner, you select everything which is completely inside this selection window. So in this case, it would be the whole right column with the nodal support and also the node on the top. Yeah. Otherwise, when you draw the selection window from the right to the left corner, then everything is selected which is surrounded by this selection window. So in this case, it would be the column on the right side, but also the steel girder and the concrete surface. Yeah, this is important to know. And yeah, with the mouse wheel, you can also zoom in, zoom out. I think this is clear. And when you press the control key on your keyboard and then also press your mouse wheel, then you can rotate this structure. Yeah, and when you press the shift key and also the mouse wheel, then you can zoom in, zoom out. We offer the possibilities also with this icon here in the icon bar. Move, zoom, rotate, and so on. There you have the same possibilities. And so on. Good. I think this was everything. Bastian, have I forgot something or do you want to add something?
I think you haven't forgot something, and there are also no questions. So I think you can move on.
Yeah, so for the participants, don't be afraid to ask us. We are glad to help. You can ask everything if you have any questions relevant to this training. So don't be afraid. Good. So now I have also prepared a question for you. And this is this one. What is RFEM? Good. Let's close this poll. I show you the results. Exactly. So RFEM is a 3D FEA program for calculating members, plates, and shells. So the first answer is correct. And now I have also another question for you. I hope you know it. Good. The most of you have already answered this question. And the most of you paid attention to that chapter concerning the general basics of FEA. So discretization, what is that? It's a decomposition of structures into finite elements. Very, very good. So let's start our example. Jump back to continuous plate. Let's start modeling it. So first of all, I create a new surface. In the symbol bar, I find this icon, new rectangular surface. And by clicking on the arrow, I find also other kind of surfaces. But for me, it's good to use this rectangle one. I click on that. A new window opens. And the next thing I'm gonna do is create the material. In this case, I use the Eurocode concrete C3037 material. For those who don't have this material here, no problem. Edit the material by clicking this icon here. And open the material library. And there I have the possibility to filter different kind of materials like concrete, metal, timber, and so on. And also the material category itself, like concrete and lightweight concrete, and also define it according to the standard. In this case, I choose here the Eurocode, because in German we use the Eurocode. Maybe when we have some people from Swiss, Chinese, Great Britain, Canada, and so on, there are also some other standards. Yeah, good. Concrete C3037. What does it mean? 3037, we have a characteristic cylinder, compressive strength of 3 kilonewton per square centimeter. This is this 30 and 37, and the other one is the cube compressive strength. I click on OK. Important note is that we set the Poisson's ratio to 0 because we want to get for that example the results which should be constant over the whole plate thickness. Yeah. So no shear deformation in the plate thickness. I click on OK. And the thickness of our concrete surface is 300 millimeter. So I click on OK. And now I draw and activate here the snap function. Now I draw this rectangle from my local global coordinate system, 10 meters to the right side and 5 meters high. Good. Now right click and I close this way of insert of a new surface. So now I see here the rectangular surface. And now I can copy it or I create a new one. Now one tip, please remember this, it helps me a lot. By clicking the enter or the return key on your keyboard, you do the same task again. So our task was the creation of this new rectangular surface. When I click the return key or the enter key, it will open this new rectangular surface window again. And I click on OK again. And I create the same surface again with the same geometry. And now I do it here again in a distance of 5 meters from the right upper corner node. So now we move this 10 meters downwards. So I select all 3 plates, snap here in the near of this middle surface, in the near of the left bottom corner, and move this to my global coordinate system, so to the are the results better, it is useful to use the same thickness of the plate and also refer it on a 1 meter beam. So we create here a new cross section for member start. And I click here the import parametric solid cross section, a rectangle. The width of my cross section is 1000 millimeters, and the height is the same like the thickness of my plate, 300 millimeters. The material is the same, concrete C3037. I click on OK, and it looks like that. Here I get the cross-section description, also with the cross-section properties, like the moments of inertia, bending, torsion, and so on. I click on OK. And now the member start has the cross-section of this one, and the member end also has the member start. I click on OK. And now I draw it from left to the right, also 10 meters long, and close it with the right click. Good. Now I can rotate it a little bit. And now I can see it from a 3D perspective. Good. So the next thing is we want to have a continuous beam and also continuous plate. Therefore, I have to create in the middle lines and also here nodes in order to create afterwards supports. So how can we do that? We can divide here this line into 2 lines, and then we get here the middle node. And then with the reference of the middle node, we can create the next line perpendicular to the other end. So you can also see here the line, the red line, and also here the arrow. The arrow shows from the left to the right side, and this symbolizes me that the starting point or the starting node is on the left side and the end node on the right side. With right click on one of the line node, I can also show me the local axis system, and this is similar to the line direction. So the local x-axis of every line or every member is the same as in the line direction. Yeah, so you see it shows to the right, to the same direction. And one important note is also that every member has included a line, but not every line has included a member. So for this case, for example, I have here this member, and I have here included this line. And yes, so here I have this member and also the line, but not every line has a member. I think this is clear because here in this case I have this surface, and these lines are just the boundary lines for this surface. Good. Let's close this local axis system. Now I want to divide this line. I click here on polyline with a right click, and I click here on divide line. And I just want to have a middle node, so I can divide it into n intermediate nodes. And when I click here 1, it will be divided into 2 parts. When I enter here 2, into 3 parts, 3 into 4 parts, and so on. So I click here on 1, and I see here this node, and these 2 lines are divided. So next thing is that we create here this line perpendicular to the next one. So click here on new line and draw this line from there to there, and double right click, and we can close this. Now it comes to my favorite way of creation of objects. Yeah, and this is the copy via drag and drop. We can easily copy this line by drag and drop. Just click on that line, press the Control key on your keyboard, and now the left mouse, and click and hold and put it to the other surface. And the same thing we do also for the other one. Good. Now let's divide this member here. Press on right click, divide member. Now you can do it by distance or graphically. I decide to do it by distance. And now it's also interesting how we can do that. We want to divide it exactly in the middle. So we can choose here 50% as relation or the absolute value. And it will start from the member start or from the member end. And now here you can see the arrow, and this arrow shows from the left to the right side. And when I want to have a division 3 meters from the start, I have to enter here 3 meters, and the member end will be calculated automatically. The same thing with member end. If I want to go from the right side, so from the member end, press here 6 meters. The member start will be resulted automatically. Yeah, but in our case, 50%, because we want to divide it exactly in the middle. I click on OK, and we get here this new note. Okay, Bastian, are there any questions? I see some questions in the chat. So should we show something again? What do you think?
I think what you can do is you can show us again how you can edit the cross section, for example, of the beam, and yeah, guess that would be nice to see again.
Okay, of course. So there are different ways to do it. You can do it with the help of the data navigator. Here you have the cross sections. Open this cross section, and by right click on this rectangle, you can edit this cross section. Click here on edit, and then you can also edit here at the description. So if you only have here, for example, 900, you can add here 900 and here 200, for example. No problem. Or if you want to create a complete new one, no problem. Just click here on any other cross sections, like for example, IPE profile, and choose one of the IPE profiles, and then click on OK, and you will have here a new cross section. Yeah, this is one way of doing this. Or you choose here the whole member by selecting this. Click on right click, member, and edit. And then you can modify your member here also by edit the cross section for the member start or create a new one. It's the same procedure like here with the data navigator. Okay. Good. I would continue. Now let's do here some supports. It's very easy. We have here line supports for surfaces and lines, and also nodal supports like here for this kind of members. So we create now line supports. We choose here this hinged support. I click on OK. Now I draw, and this is now the big advantage of RFEM. I can choose and select several objects at once. So I rotate my my interface a little bit, and now I draw a selection window now from the right to the left side in order to get all three middle lines here. And the same thing I do also with the other surfaces. Good. Now let's come to the member. Here we do two different kind of nodal supports. The first one is a new type of nodal support. So therefore I click here on new type of nodal support. And now let's watch here this definition of support conditions. So if I activate or I check one condition, like here UZ, then I activate the deformation of UZ. So no deformation in this direction is possible. So therefore there will be some forces. And the same also with restraints. So the same also with, now I have to look it up, this word, for twisting and also for moments. Yeah. So in order to prevent that torsion or the twisting of my member, I have also to activate the restraint phi x. Yeah. So this will prevent me a torsion around the x-axis. Good. Now click on OK. Draw a selection window for just for the first node on the left side. And for the other two nodes, you can now draw also a selection window. And it is no problem that the member is also selected, because we want to create now an object just for nodes, and the program recognizes it. So click here on new nodal support, and now we can choose the normal hinged support. And because we have already selected the nodes here, the nodes appear here also in this box. Click on OK, and the two supports were created. Okay, good. Now, the next part or the next step is the creation of loads. Before we do or add some loads, we have to create load cases. Yeah, so click here on new load case in the symbol bar. You can also do it here, load cases, combinations, new load case. Same procedure. As you can see, we have more possibilities to insert something or to create something. So new load case. And for our simple example, we insert the name or the description test load and deactivate the self-weight, yeah, in order to compare the results better. So then I click on OK. And I will create here surface loads and here member loads. So again, new surface load here in the symbol bar. Here I can set up some load types, load direction, uniform, so the load distribution, linear in X, linear in Y, and so on. I add here the magnitude of 10 kilonewton per square meter. Maybe the load direction is here closed or grew up, so growed, because we use the model type 2D, so there we have some restrictions concerning the load direction. Yeah. I click on OK. And I add here the loads on the surfaces. Says, good. And now let's do the same for the continuous member. One big mistake, especially for RFEM beginners, is to use also line loads for members. But we have to use member loads for members. Line loads are used for additional loads on lines. So when I have here, now I have to look it up, the word, a railing or a handrail here on this line, and I want to add here some loads, then I can use here the line load. Or when I want to have here the consideration of wind loads, and I consider it here at lines, then I can use here line loads. But when I want really to load members, I have to use the member load. Please keep that in mind. Yeah, that for members I use member loads. So I click here on member loads, enter here the same load parameter, so 10 kilonewton per meter. Click on OK, and I choose here both members. Good. And the display of the member load, I can do it a little bit smaller, so I decrease the size here. So now it looks good. Nice. So the next part is the creation of the refinement. So every surface gets a different mesh size. In order to do that, I create here FE mesh refinements. Normally, the whole settings of the FE meshes are managed here at the Calculate tab under FE mesh settings. Here you set the general target length of the finite elements. So if I would do nothing, every surface would get a finite element length of 0.5 meter. But in this case, I want to have for every surface another one. So I do here FE mesh refinement, right click, new FE mesh refinement. I choose here at first surface, target FE length 1 meter. So we get 1 meter big meshes. And now I have to choose the surface. And in this case, I choose the first surface. I click on OK. And click on OK again. Now, let's do the same thing again. Right click here in the data navigator, new FE mesh refinement 0.5. 0.5 here at the target FE length. And the surface is this one. I click on OK. On OK again. And now here we do a different way of insert. Right click, FE mesh refinement, new. Because we have already selected it, it shows me here that we have this third surface. We create a new FE mesh refinement 0.1. Okay. Here we see the FE mesh refinement with this quadratic object symbol. Yeah, and now I would suppose that we calculate it. And before we do it, and in order to compare the results better to each other, it would be quite helpful if we have sections here at the surfaces. In order to do that, here in the data navigator, we have also the possibility to create sections. Just right click, new section. The section name is 1-1 or something like that. You can also do A, or whatever. It's up to you. The sectional surface, so the projection direction is here, the global z-axis. Please, okay, I think local and plus z is okay, but please only on surface 1. Okay, and now I have to set or choose the edge points of the section. This will be the middle of this line to the other middle of this line. And I click on OK. Now I see here the section. Maybe I can disappear the loads here by clicking not to show the loads. And now also one of my favorite ways of creations or something like that in RFEM is drag and drop. So press Ctrl key, left mouse click, and copy it from one side to the other. So from one surface to the other surface. So, and modify or edit here the section name and choose here the correct surface. And let's do here this thing again. Choose here also the correct surface and click on OK. Good. Now I think we have everything. What do we need for our calculation? The next thing is starting the calculation. Therefore, you can use here calculate all in the symbol bar, or also here calculate RFEM results only, or to calculate, and there you can choose your load case or your load combinations and so on. The topic of defining load combinations and so on will be part in the next chapters, in the next parts of our student series of online training. So I click here on calculate all. And the first thing what we gonna see are the deformations. So here the deformation, and also very nice thing is when I change here the display model to the wireframe display model, I see here also the size of the FE meshes. And as we said before, here in this first surface, we have a FE mesh size of 1 meter, 0.5, and 0.1. Good. In order to see the results here at the beam, we have to activate members, and we see here the bending moments. Field moment, support moment, also the shear forces and so on. But I think this is clear. More interesting are maybe the sections of the surfaces in order to see the bending moments of the surfaces. Therefore, I activate here in the result navigator sections, and I want to see the bending moments. So I have to activate here surfaces and choose here MX. So one hint to the basic internal forces of these surfaces. You can see here also the local axis of every surface. And at the moment, I deactivate maybe for the moment the results. Just see what I want to explain you. Here we see the local axis of this surface, the x-axis and the y-axis. Yeah, the x-axis shows to the global x-axis, and the local y-axis also to the global y-axis there. So now, important point, the basic internal forces like mx and my, they are located in the same direction like here. Yeah. So mx is along to the x-axis, to the local x-axis of this surface, and the same for my. The opposite of that is the member, because here we have my, and when we take a look on the local axis of the member, here the bending moment is around the local y-axis, and other here at the surfaces it's along the local x-axis when I watch the mx bending moments. Yeah, so keep that in mind. Surfaces along and members around the local axis. This is important to know. Good. So let's watch the results together. So here we can see, okay, the results are pretty okay, especially the one here with the fine mesh. There we have the same support moment like here with this member. Okay, this looks pretty good. In general, the results are quite good. Yeah, especially the extreme results, like here the field and the support moment. But now this will be very important. The length of this FE mesh, here you see it's linear, and normally it's everywhere linear, but here we have in 1 meter just one FE mesh, FE mesh, yeah, FE element, sorry, and here we have 10 FE elements in 1 meter. So the approximation of the results will be here very incorrect, I would say, or not really exact. And here it's more exact. You see it here at the distribution of the moment section, yeah. And it isn't really exact in comparison to that one where we have really fine FE mesh sizes. So keep that in mind. The extreme results can be correct almost, yeah, but the results between that extreme results can be at the more rough finite element, not so good, like in one FE element. This is what is really fine, yeah, because when you compare maybe the two sections together, result diagrams, and I watch here this one. So the first section we have here basic somewhere at 0.57 kilonewton meter, and here also 0.5, almost 8. Yeah, so this is a difference, and this is something to remind. Yeah, so you have to know it. I would suppose you do that FE mesh quite fine, yeah, but not too fine, because when you have too fine FE meshes, then the calculation will take very long. So you have to find the right, the right proportion, so the right FE mesh sizes in order to have correct and exact values, but also consider the long calculation of FE programs. Yeah. Now I see one question, and this question is, what is suggested FE mesh size? I would recommend you to have at least 4 up to 6 or 8 FE meshes in one surface. So we have here from there to there, it's 5 meters. So at least there should be from one boundary condition to the other boundary condition, at least 5 up to 6 meshes, finite elements. Yeah. So I would say this one is quite good. This with the mesh size 0.5 meters. This one is very fine, and it is not so important to have so fine FE mesh. Yeah. And another question I see, are there any shortcuts for show or hide loads? No, unfortunately not. There are no shortcuts for that kind of things. But maybe Bastian, you could find other shortcuts for other type of functions. This would be good if you could post it as an answer for that question.
Okay.
Good. Now, normally in the study, you do some hand calculations. That's pretty in common. And therefore, you use also some tables or calculators and so on. And when you calculate the support moment of a two-field beam or continuous beam, you will get maybe other kind of values. So let's watch the results again. And normally you would get here support moment of 31.25 kilonewton meters. Yeah, but in this case, just 31.18. Why? It's due to the shear activation of members. So I go here to calculation parameters. And here you see the activation of shear stiffness of members. If I activate it, it considers additional shear forces and therefore also additional deformation. And you calculate it as not as stiff. So in Germany, you would say schubweich. Yeah. So with the activation of these cross-sectional areas AY and AZ, so additional areas of cross-section. So, and this will be very interesting for the next chapter now, because I have also prepared a PowerPoint for that. So I jump back to my PowerPoint. And now I want to take a look on the plate theory. So first of all, we try to take a relevance to the beam element. So on the one side, we have the Bernoulli beam, and on the other side, we have the Timoshenko beam. The Bernoulli beam says, okay, the cross-section remain in play, and also the cross-section remain perpendicular to the member axis. And we don't consider any shear deformation. So we have really rigid shear stiffness. And when you calculate something in the study with tables or something like that, you will calculate a Bernoulli beam. Yeah. But what is the most case implemented in the FEA programs is the Timoshenko beam or also the other plate theory. But at first we take a look on the Timoshenko beam. The first case or the first condition is the same. Also here the cross-section remain in plane. and also the cross-section remain perpendicular to the member axis. But what we consider here is or are shear deformations. So the shear stiffness is limited and not rigid anymore. So here it remains perpendicular to that axis. And here we get an additional angle. So it won't be perpendicular anymore to the member axis. So additional deformation to this Timoshenko theory. Now let's transfer the beam theory to the plate theory. The Bernoulli beam is in the plate theory the Kirchhoff theory, and the Timoshenko the Reisner-Mindlin theory. So what are the conditions? We have a geometrical linear system, so small deformation, also the Hooke's law, cross-section remain flat, no warping, and also a constant thickness. And we don't consider any shear deformations. Reisner-Mindlin, the four are the same, but we consider shear deformations and also the transverse and lateral strain. What is that last one, the transverse or lateral strains? When I have here this kind of beam and I try to tie this beam with a force, it will get a little bit longer. So that part, the thing where it gets longer is called delta L. And also the cross-section becomes a little bit smaller. Yeah? And this effect is called the transverse or lateral strain. In German, we would say Querdehnungseffekt. So again, as a summary, Kirchhoff on the left side, Reisner-Mindlin on the right side. Kirchhoff is the same like the Bernoulli, and Reisner-Mindlin the same like the Timoshenko beam. So at Kirchhoff, we don't consider any kind of shear deformations. And at Reisner-Mindlin, we consider shear deformations. So what can we use for Kirchhoff? We can use Kirchhoff for the theory of thin plates. So normal concrete surfaces, like in the story buildings or something like that. There we can get quite good results for the Kirchhoff theory. It's a simplified approach. And the Reisner-Mindlin theory, that we consider the shear deformation, and we can use it for thick plates as well as for thin plates. So when you calculate according to the Reisner-Mindlin theory, we will get, as well as for thin and thick plates, quite good results. Because it's a higher value approach, and we get also more accurate shear forces. So my recommendation for you is, please use Reisner-Mindlin, because then you get for almost every kind of application areas quite good results. Yeah, because when you use Kirchhoff for very thick plates, like plates with a thickness of 2 or 3 meters, like foundations or something like that, then the results won't be so correct. Good. Now let's jump back to the RFEM. And now let's see what's gonna happen when I change here at the calculation parameters. The activation of the shear stiffness of members. So I deactivate it. Now I calculate according to the Bernoulli beam. So no shear deformation. I recalculate it. And I will get the support moment of my two-field beam of 31.25. And this will be also the same when I calculate it according to tables, or when I do this by the force method or by hand. Yeah, so keep that in mind. Okay, Bastian, are there any questions?
I don't think you missed something. We have no unanswered questions. So, well, I don't know if feel free to ask. Oh, wait, there's a new one. But I think that's better if I answer this by my own, because this has not that much to do with the online training right now.
Mm-hmm. Okay, good. So I hope you paid attention. I have prepared a question for you concerning the activation of the shear stiffness. Please answer the question. Okay, let's close this poll, show you the results. So the most of you were correct, because the shear stiffness is activated and then the shear deformations are considered. Exactly. Very good. I am happy with you. Good. Now let's jump to the next chapter, and this is the Euler case 1. So this hinged beam. No, this is not a hinged beam, this is a clamped beam, and this clamped frame. Okay, so let's go ahead. I create a new file, a new model here in RFEM, new model. And in this case, I insert here Euler case 0.1, save it under downloads, and very important now, I want to consider a 3D model, because we calculate, or we do a stability analysis of this Euler beam, and there I want to consider both buckling directions. So therefore 3D, I click on OK. And what gonna we do now is creating this column. Therefore, click here on new single member. Click on create new cross section for member start. And we choose here a steel profile, what is very common in Germany. HEB 300. So I click here on import roll cross section HEB, or when I can't find it here, you can also import cross section from the library. click here on I sections. And choose here this HEB. So what are HEBs? These are wide I-beams with parallel flanks. Yeah. And we choose here this HEB 300. Material is steel S235. We can also edit this material. I choose here this steel material according to the Eurocode. You can also import some material from the material library. Steel S235 because of this yield strength of 23.5 kilonewton per square centimeter. I click on OK. Again, and now I want to create this column, and this is also maybe one of the mistakes when I want to create a column and I'm not in the correct work plane, that I can't model it into the height. Yeah, it does work because I am here in this work plane. Two possibilities. I change the work plane, for example in XZ, and then I draw it 10 meters high. Or if I want to stay in the same work plane like before in the XY, I have also the possibility that I create this beam with the help of the length and direction. And now I say, okay, perpendicularly to the work plane, 10 meters high, and the opposite of the global Z direction, and I have the same result as the left beam. Okay. This is one tip. I delete the right column, and now I will add here this support, nodal support. In this case, we have here rigid support, so the whole node is fixed in every directions. So there will be horizontal and vertical forces and also bending moments around all axes can be transferred into this nodal support. Good. Now, this was everything concerning the creation of modeling. Now we create a new load case. Again, load case will be test load. And we don't consider the self-weight again. And I click on OK. Now we create a new nodal force. So, and on that node here. So, therefore, we click here on new nodal load. You find it here at the symbol bar, new nodal load. And this nodal load refers to the global coordinate system. I put here a horizontal force in the global x-axis or x direction of 10 kilonewton and vertical force 100 kilonewton. I click on OK and press or select the head node here. Good. Now let's calculate this thing. Show results or calculate all, doesn't matter. And what gonna we see now is the deformation. And in this case, the deformation is shown as 63.5 millimeters, we can show us the deformation also a little bit nicer. Therefore, we go to the display navigator, scroll to the chapter results, and jump to the chapter deformation, members, and I want that the cross sections are colored. So I click here and we see the cross section colored. Also the deformation of the member. Okay, I think the deformation is pretty clear. We have here this horizontal deformation, mainly, maybe also a little bit pressed. Okay, good. Now, also interesting thing is the calculation theories. You know, maybe the calculation according to the first theory of order, then also the second theory of order, and so on, all the p delta. Yeah. And when I do the calculation of load cases, then I calculate, or I build the equilibrium of the system at an undeformed system. The second theory of order calculates me the equilibrium at a deformed system. Yeah, and there can be some differences, especially when I'm talking about the internal forces like the bending moment. Yeah, and therefore I want to show you the differences maybe. Yeah, so I will create 3 windows in order to show you the results of this column a little bit better. So I click here, new window. Again on a new window, and I show me now the windows in 3 windows. So perfect. I change maybe the view in the opposite of the y direction. Perfect. So what we gonna do now is go to calculate here in the menu bar and go to the calculation parameters. And go to the register load cases. And there we have our load case test load. And normally the load cases in RFEM are preset with the theory of first order. So we have there a geometrically linear analysis. Now we're gonna do a nonlinear geometrical analysis. So we choose here the second order analysis, p delta. Yeah, I think especially the American guys knows this as p delta. I click here on second order and I calculate it. So let's calculate it. And maybe you see also here the deformation. They are a little bit different, but this is not the main point. I take a look to the bending moment, especially at the bottom. There we have 106.87 kilonewton meters. Normally, we have a length of 10 meters, a horizontal force of 10 kilonewton, 10 multiplied by the lever arm of 10 meters is 100 kilonewton meters at the bottom as internal is a bending moment. Yeah, so you don't have to do it again. I will show you the internal forces again at the analysis of a geometrical linear analysis, so theory first order. Here 100 kilonewton meters. Now again with theory second order. And now we get additional 6 kilonewton meters. Yeah, where does it come from? As I said, the geometrical nonlinear analysis, according to the theory of second order, is the calculation of the equilibrium at the undeformed system. And now let's take a look to the undeformed system. The horizontal deformation here at the head node is 68.7 millimeters. Now when you multiply it with the vertical force of 100 kilonewton, you will get an additional bending moment of 6.87 kilonewton meters. Results to an overall bending moment of 106.87 kilonewton meters. So 10 kilonewton multiplied by the lever arm of 10 meters is 100, plus the 100 due to the deformed system. 100 times 68.7 millimeters equals 6.87, and as a sum we get here 106.87 kilonewton meters. So far to the different calculation methods. Good. Now let's come to the stability analysis. And this is also very important, especially when you are dealing with steel structures. There you will need it. So first of all, I will create only a vertical force. So I will delete here this horizontal component. I will show me the grid again. And for stability analysis, in order to get the buckling or the eigenforms or the critical load factors or the critical loads, critical lengths, you have to use one of our add-on modules, and this is RF stability. You find RF stability here in the DETI navigator. Scroll down. Here you will find it, RF stability. Or you find this also here in the menu bar, add-on modules, stability, RF stability. So this new window will open, and what you can do with RF stability. With RF stability, with RF stability, you can do any stability analysis by the eigenvalue method. So you can calculate eigenforms, buckling forms. You can get the critical lengths, critical forces, critical loads, and so on. And this is very good in order to detect maybe some weaknesses of your structure, or in order to detect some critical points and so on. Therefore, it's very good. And now let's do the typical Euler case number 1. And in the study, I think you have already learned how the first eigenform or the critical with the buckling of one Euler case looks like. Let's do the same here in RF stability. So first of all, number of lowest eigenvalues. In this case, the Euler case 1, there are only 2 cases important. So I choose here 2. We have the buckling around the weak axis and the buckling around the strong axis. We choose here the load case 1. We don't need to consider favorable effects due to tension and also no free stress for cable and membranes. But I would activate the division of straight members and would set the minimum number of member divisions to 10. So then you have also additional information concerning the calculation method, but normally the method by Lanchos is quite good. Okay, then click on calculate. And now you will get different results. On the one side, you see the critical load factor. The critical load factor shows this for each eigenvalue. If the factor is less than 1, this means that the structural system is unstable when you calculate it geometrical nonlinear. Factors greater than 1 means a factor greater than 1 means that the loading from the given actual force multiplied with those factors results in system failure due to buckling. So this means when I have critical load factors which are under 1, then you will get an unstable system. Greater than 1, it is stable, but you have to pay attention to stability and you have to consider the stability cases. Then I have also the magnification factor. The magnification factor describes the relation between the moments according to the geometrical linear static and the second order analysis. So when I have a bending moment of 10, for example, and I calculated this bending moment with the theory of first order, now I multiply this by the magnification factor by 1.291. Then I get the bending moment according to the second order analysis. Yeah, so I have 10 kilonewton meter according to this first order, multiplied by 1.2, so 12.9. I get the bending moment according to the theory of the second order. Good. Then let's jump to the effective lengths. Here I have the effective length, so the buckling length, yeah, and the critical load. The critical load tells me how much normal forces can resist my column in this case, or my structure. When I have more than 443 kilonewton, then it will collapse. Under that 443, it's okay. Okay. Now again, so as a summary, so critical load factor. The critical load factor says, okay, with which factor I have to multiply my system, so my loads, in order to get an unstable system. So if I multiply the 100 kilonewton vertical force with 4x434, then I will get a critical load of 440 kilonewton, and then my system becomes unstable. So let's watch the eigenforms graphics. So the first eigenform of this column is the buckling around the weak axis. Yeah, you can see it here. The weak axis is the z-axis. So around the weak z-axis, my system is buckling, or so this is the first eigenform. Now the next eigenform is around the y-axis, because the y-axis is the much stronger axis. I think this is pretty clear. And therefore, because the strong y-axis can resist more loads, therefore the critical load factor is higher, and also the critical load is higher. Good. Now let's see what happens when I increase the load of 100 kilonewton to 443. So still under my critical load. So 443. Let's calculate this thing, calculate all, because when I have also open an add-on module, I have to click here, calculate all, in order to get results from every load case and every add-on module. Good. Okay, RF stability. Okay, now we can see it. The critical load factor is exactly 1. So this means that the system is with that load of 443 kilonewton almost unstable. Now let's see what happens when I increase the load to more than 443 to 444. Now we get the result and then calculation error. The stiffness matrix is singular, the model is unstable. And this is the reason, and that the model is unstable because of that too high load. Yeah. So this case, my system is unstable, the stiffness matrix is singular. For that, we have a very good FAQ. Bastia, maybe you could put the FAQ to the chat, and this FAQ will help you to find maybe also the problems or the critical locations why your model is unstable, especially at the beginning of modeling with RFEM. It can be possible that you find this problems. Okay, good. Now, I have prepared for you 2 questions. First of all, this one. Okay. Maybe let's wait for the other one. Only 70% have chosen the language, the answer. Okay. So the correct answer is the first one. The plate theory of Kirchhoff considers no shear deformation. So that's correct. And now I have also prepared another question concerning the critical load factor. Okay, let's close this poll again. I show you the correct answer, and the most of you have chosen the correct answer. So again, the critical load factor says at which load I have to multiply the critical load factor in order to get this system unstable or until the structural system fails. Good. Now, let's jump to the last chapter of this training, the modeling and analysis, also stability analysis of a clamped frame. Therefore, I change here the nodal force to 100 kilonewton back. And a big advantage now in RFEM is that we can easily copy something. Therefore, I select the whole column, right click, and I say move and copy. Now, it's important when I want to copy something that I put here a number higher than 0. And the displacement vector is 10 meters. I can put here 10 meters as number, or I can also select 2 points in order to get the displacement vector. In this case, I choose here this length and this length. It's the same. Good. Now I need here a girder for the frame, and therefore I create a new cross section. In this case, also a new single member. I click here in the symbol bar, new single member, and I create a new cross section for the member start. In this case, I choose the IPE 300 profile. I can also enter here this in the cross section description. Material remains steel. Click on OK and draw it from the left column to the right column. Okay, good. Now I want to change the height of this frame. Therefore, I select both nodes, right click on the member, doesn't matter, member or nodes, and then I can choose here the nodes and say, okay, I want to edit it. And because they have the same coordinates, I can modify here the Z axis, so the Z coordinate. And I choose here -6. So what was the mistake? The mistake is, I'm sorry. The mistake was that I also deleted the minus, and now the system was orientated according to the global z-axis, and my global z-axis is located downwards. Yeah. Therefore, also the coordinate z plus 6 goes in this direction. But I want it like that, -6. So, but no problem. You can change it afterwards very easily. Good. Now, the same thing again. Let's do the stability analysis. Therefore, click here on RF stability again. And now we show us a little bit more eigenvalues. 6, for example. Calculate it. And now let's watch the eigenvectors. We can see that we have a deformation out of the plane. Yeah, and normally this isn't so good for frame structures or for steel hulls, and we try to prevent these situations. Jump to the next eigenvector. Here the same. We have deformation out of the plane, so the eigenform shows out of the plane globally, so the whole system. The third eigenvector is that eigenform that we know maybe also when we have eigenforms in plane. And maybe also watch the other one. This is also out of the plane. Yeah. How can we prevent this failure out of the plane? There are two possibilities. When I want to calculate it just 2D, and I can assure that out of the plane, buckling out of the plane isn't possible. Then I just change here at the general data, right click, general data, the type of model to 2D, XZ. Let's do it. Calculate RF stability again. And now let's watch the first eigenvalue, and this is this one. Yeah. And when I switch to the other ones, only in the plane, and so on. So, but how can I prevent this when I have a 3D model? Because normally structures are in 3D. So, general data, 3D again. I can add here additional supports who are carry loads from the global y direction. So I select here the upper nodes, create here new nodal support, and now I want that this nodal support carries only forces in the global y direction. Therefore, create new type of nodal support. I activate the deformation in this direction, and in this case it's UY. I click on OK, and let's see what's gonna happen if we have the same cases. Again, the first eigenvalue is here, this one. Next one is this one. This is out of the plane, but only the column, not the upper girder here. Yeah, and this is important to know. So this is more a local, it's a local failure. This is a global failure. Okay, this is important to know. Good. I have forgotten one thing, honestly. I'm sorry about that. It can be possible when you take a look to the effective lengths, yeah, you can use them also for stability analysis for this steel design, for example. And when you calculate this with your hand calculation, and when you compare the results, it can be possible that your member length, sorry, not your member length, your effective length calculated by your hand and the result by this program can differentiate. They can be different. This is because of the activation of the shear stiffnesses. Yeah. So let's take a look to the results maybe. Effective length. So remember just here, this one, effective length, 9 meters, okay, 9.163. When we change here the calculation parameters, and deactivate the shear stiffness and calculate this again. And take a look to the results. We see here different effective lengths. This is due to the shear stiffness. Yeah, so keep that in mind when you want to compare your hand calculation with the results of the program. So what does this mean? Effective length, L critical, Y. So first of all, effective length effective length factor 1.5. So you have to multiply your member length with the effective length factor 1.3 in order to get the effective length. So when you calculate 6 meters times 1.5, then you will get 9 meters. Yeah, and 9 meters is this. Oh, sorry. Nine meters is this member length here. So you have to imagine that this is the member length here, something like that. Yeah. Good. Yeah, I think this was everything. Bastian, are there any questions, or should I show something again?
There's no specific question, but maybe you want to show us how you can create a joint in the beam, or a joint connection between the column and the beam.
In general, when you use the beam type, every member has a member type, and this is the member type beam. This means that every member is connected to the other one rigid. Yeah, so no hinges, stiff connections and stiff joints. When you want to add some hinges, like member hinge or also kind of springs, you can add here member hinge. Yeah, let's do that. So we suppose for the upper girder here at both ends hinge. So hinge tells me that we don't want to transfer any bending moments to the other part, just shear and normal forces. So therefore I have to activate here Phy and Pz, and the same also here for the member end, because when you can remember, every member and every line have one starting node and one ending node. Yeah, and also the member direction. In this case, the member direction, according to the local X coordinate system, shows from left to the right side. So on the left side, I have the starting node, and on the right side, I have the end node. Therefore, I will get on both ends this member hinge. So now you see here this this white node, and now see what happens when I calculate it. Maybe concerning deformation. Maybe it would be better when I have a distributed load there. Then you can see the results a little better. You see here the deformation. I think that's pretty clear. And also the bending moment. Yeah, at both ends I have no bending moments. And the same thing, this when I have one beam which has on both ends member hinges, then I can create, instead of this beam with this both member hinges, also another member type. I can create here this truss member type. We also offer other kind of member types, but we come to that member types in the other parts of the training. So I choose here truss. Truss means that I have on both ends also hinges. I click on OK. Remember the 125 kilonewton meters. I click on calculate. And you will get the same result. Yeah, good. Bastian, any other question?
No, you just you just solved the last question by using this task member. So no more questions.
Okay. Very nice. Now I have prepared the last question for you, Paul. Please answer me that. Okay, let's close this and I will show you the results. So this was there was it possible to choose more solutions? Yeah. So which support conditions do I have to activate at the 2D system when I want to have just horizontal forces? So in general, it's like that horizontal forces are, X and Y forces. So therefore you have to activate Px and Py. Honestly, I'm sorry for the bad question. Now I see it myself. This question is formulated very unclear. I'm sorry for that. But what I wanted to ask you is, so maybe I show it to you here at RFEM. So when I want to have a support node which has only horizontal forces, yeah, then I have to activate here px, so px and ux, these two one here. Yeah, I am sorry for that bad formulation of this question. But when I have something like this, then horizontal forces in X and in Y direction are considered. Yeah. Okay, good. So let's come to the last part. I want to show you our website a little bit. So if you have any questions or issues, don't hesitate to contact us. Yeah, you can put your question every time here on ask individual question or something like that, or you can contact us also here, info@dlubal.com. There you can write us about any problems. We will help you. Yeah, maybe also interesting to know is other online training. So if you want to take part to the other online training of RFEM for students, then please register here for the second part and also for the third part. Also, one nice thing is we offer also a lot of structural analysis models to download. They are completely free. You don't have to pay anything. You can download more than 1,000 structural analysis examples from our website. Just click on one of these steel holes, for example. Click here on steel hole and click here on download, and then you can open it in RFEM and see how other engineers or other users modeled here this steel hole. This is especially useful for beginners or for those guys who are starting with RFEM. Also, you find here some online manuals and education. We have also a new e-learning platform where we added 3 new playlists: student lessons, short video tutorials, tips and tricks. Visit them, you won't regret it. And also infotainment for those who are interested in the most important formulas of a civil engineer. Click here on Good to Know and watch the most important formulas for a civil engineer. I will post this in our chat. And watch the video. Maybe there are some useful tips for your future career as a civil or structural engineer. Okay, so now I see there's some question. Is it possible to watch the full lesson again? Will you send the recording? Of course, you will get the recording tomorrow. We will send you a mail. Hi, can you show us how to calculate truss stability? The calculation of the stress stability is almost the same. There's no big difference. Yeah. Why we need Vz for beam hinge in previous example. So first of all, the calculate truss stability, almost the same. Yeah, no differences. And so on. You can calculate this as well. Now let's jump to the continuous plate. And there was one question, why we need Vz for beam hinge in previous example. I think you mean this one. So this nodal support. Oh, come on. This one, I can tell you why. Because when we calculate this like that, then it would rotate, the beam would rotate over his own axis. So this would cause an instability. I can show it to you, and therefore we have to close this directional deformation. Otherwise, it won't be possible to calculate it. Yeah, stiffness matrix is singular, instability found. Structure is unstable, instability found in FE measure of the direction phi x. Therefore, we have to close this possibility of movement. And then it works. Okay. So now the other question, can you model two-way slab in 3D and compare it to hand calculation? We will do this in the other parts of training. And yes, today's training or webinar was free for students. Exactly. So, Bastian, anything to add? Or do you have something?
You were too fast. Because, yeah.
Sorry, Bastian. No, but I would say that we have everything. Do you? What do you think? Good. Then I would say, have a nice day. We would finish here this training and have a nice day, also a nice week. And also good luck for your exams, for example, or also your study. Have fun also with training in RFEM. And I hope we see us the next time. And with these words, I say goodbye and stay healthy.